Hey guys, hello everyone and welcome to the channel and welcome to yet another video of single shot video series. In this series we are taking some simple topics which can be discussed in a single video of 20 to 30 minutes. We have already done 7-8 videos on the channel. You can watch them in the playlist. I'll give you the link of the playlist in the description of this video. We have already done topics like nuclear chemistry, polymer chemistry, solid state chemistry, electrochemistry and much more. So you can go to the playlist and watch those videos as well. In this video I'm going to take analytical chemistry and some of the topics from analytical chemistry which can be discussed, especially some analytical techniques. That's what is going to be discussed in this video, because some text based or some some statement based questions are asked from analytical chemistry. So we'll try to cover that up in this particular video. The slides of these videos are provided by Karthik. Some of the modification I have done on it, but most of the part is provided by Karthik. So a big shout out to Karthik. Thank you so much, Karthik, for providing these slides. Now, without wasting any time, let's continue with our video. Alright, so the basic definition of chromatography says that it is derived from a Greek word called chroma, which means color, and graphene, which means to write. So chromatography is a technique where we use color to understand, or color as a tag to see that where what it is. Okay, so the principle of chromatography is basically a separation. So chromatography is a separation method where the analyte is combined with a liquid or a gaseous mobile phase. So analyte is something which is being analyzed, okay, and which is pumped through the stationary phase. The stationary phase means something which is not moving. Usually one phase is hydrophilic and the other one is lipophilic. Okay, so these are various different terms over here, but you have to understand that in chromatography you just need something where most of the things are stationary, they are not moving, and this is where your analyte is lying, and you try to give a mobile phase, means you try to move something around it, so that whatever is stationary and whatever is not moving, with the influence of this mobile phase or whatever is moving through it, the thing which is not moving at all, or the thing which is in the stationary phase, also moves a little bit and gets separated from each other. Okay, so the component of the analyte interact differently with these two phases, means the stationary phase and mobile phase. So they interact differently over there. Depending upon their polarity, they spend more or less time interacting with the stationary phase, and thus retarded as a greater or lesser extent. This leads to the separation of different components present in the sample. So let's say if there are three components mixed with each other, so some component will be intact with the stationary phase more, and some will not be intact with that much more. So when you are moving the mobile phase, or when you are moving the liquid through this, so the one which is not intact properly with the stationary phase will move with the liquid a little bit, and that's how it will be separated from the other two. Okay, so that's how we separate it. So each sample component elutes from the, elutes means comes out or separates out from the stationary phase at a specific time, its retention time. Okay, so that time is called its retention time. As the component pass through the detector, their signal is recorded and plotted in the form of chromatogram. Now there are different types of techniques, so depending upon different of them, we will have different types of signals which is been recorded, and differently the chromatogram is also going to work. There are basically four types of chromatography: adsorption chromatography, thin layer chromatography, column chromatography, and partition chromatography. So partition chromatography, or also called as paper chromatography, is where the stationary phase is water trapped inside the pores of cellulose paper. Mobile phase is the solvent which is used. So special Whatman paper, okay, that's the special name of that paper, which contains cellulose fibers, high quality, and gives better result. So these are the properties of Whatman paper. So yeah, so that's what it is. And the modified papers are also used. The modified papers are hydrophobic, hydrophilic layer is applied on the paper, on the Whatman paper. So the principle is that partition liquid, that is in the normal paper, whereas if you have to separate out solid liquid, you use modified paper. Okay, so modified Whatman paper. Now solvent rises via the capillary action. Capillary action means slowly as the paper is there, so water is going to rise into it. If you dip a paper into water, what happens? The paper soaks the water, right? That's called the capillary action. So types of paper chromatography is given over here: ascending paper chromatography, descending paper chromatography, ascending descending paper chromatography, and radial paper chromatography. and 2D paper chromatography. So all of these are shown over here. You can see in the ascending paper chromatography, the solvent is going to rise up. In the descending one, the solvent is going to flow down. So this is the descending one. Okay, so mobile phase is kept upside, and the water is going to get soaked into the paper, and it is going to move downside. Whereas in the upside one, or you can say ascending paper chromatography, the solvent is kept downside, and the solvent will slowly go up in this particular paper. And then you have ascending descending paper chromatography. So this is ascending descending. Okay, so first it will ascend and then it will descend. So it is used when the flow of the fluid is very fast. So that's where it is used. Radial paper chromatography is the circular paper. Sample spot is at the center. Just like this, you can see the sample spot is at the center, and the components are radially separated. So here the separation will be like linear. That means the layers will be separated like this, but here the layer will be separated in the form of circular rings around the spot. And 2D paper chromatography, here the paper is rotated by 90 degrees to get a 2D separation of the component. Let's talk about the RF value. What is RF value? So RF value is unique for each component of the mixture, and hence it can be identified by the comparing it with the literature value. So the exact value is there already, like lot of values are there in the literature. So you just have to calculate the RF value, and then you can compare with it to find out that what exactly is there in your solvent. So let's say if you are calculating, RF means retention factor. Okay, RF is called retention factor. So RF is calculated as distance traveled by the component divided by distance traveled by the solvent. So let's say this is the paper which we have, and this is the spot which sample you want to do the chromatography. Now you will dip this salt into the liquid. Let's say there is the liquid in which I am dipping it. So this is the liquid, or this is the solvent which I am dipping. So slowly this solvent will rise into the paper, right? You will keep it for, let's say, 1 hour, 2 hour, 3 hours. So the paper, the solvent is going to rise up, and along with that that liquid, this spot is also going to become broader and broader. Okay, so this will broader, and at the end, let's say it reaches to this point. So this is the final position where the component has moved. So that is A. This distance is for the component which is moved, but the water or the solvent is not going to stay up till here. The solvent will move much further, and it will move to the point which is called solvent front. So we actually, whenever we do the paper chromatography, we keep the paper into the solvent for a longer duration, so that the solvent reaches to the solvent front. That means it should travel the whole distance here, and then we see that how much the spot has traveled. So when you divide the distance traveled by the component divided by the distance traveled by the solvent, A upon B, that is going to give you the RF value, or the retention factor value, for that particular spot, and then you will be able to find out that what exactly has been separated out from the spot or from your sample. Okay, next is TLC, thin layer chromatography. Those who do organic chemistry, they are like, they have to do TLC all the way long. Like every time in their labs, they have to do TLC before doing any other chromatography techniques. So this is the preliminary chromatographic techniques which is being done, so that you get to know that how longer or how bigger the column, the silica column you have to pack for the separation of your compound. So here the mobile phase is liquid, stationary phase is solid, which is the adsorbent on the TLC plates. TLC is thin layer chromatography. TLC plates are like commercially available, so people purchase it to do it further. It separates the component on the basis of polarity. In our adsorbent is polar, then more polar component travel less, and less polar component travel more. Okay, it's simple as it is. And the adsorbent examples are silica gel or alumina, etc. So same as paper chromatography, RF value is also calculated here as well. So everything is same. The only thing is that instead of paper, you use thin layer chromatography plate or TLC plates to perform TLC, and other things are same as what you do for the paper chromatography. Why is it so important? So it is important for visualizing the colorless spots. So if the spot is not colored, let's say the compound is not colored, so you won't be able to use paper chromatography. In that case, you have to use TLC plates, and then you have to use UV light to see that how much that spot has traveled. So in UV or in ultraviolet lights, a light, that will be useful. And also you can use chemical, because many papers might react with the chemical, right? But TLC plates are not going to react. So concentration affect the separation and the visualization of the spots. Low concentration spot will not appear, whereas high concentration you might get strong streaks. So you have to consider, or you have to take appropriate concentration so that the separation becomes quite easy to see. Size of the thin layer adsorbent is about 0.2 millimeter. The TLC plate is made up of aluminum sheets or glass slides lathered with uniform layer of adsorbent. A colorless spot can be detected using iodine crystals or in the UV light. Next is your column chromatography. The next step after TLC or after paper chromatography is to go for column chromatography. So here the stationary phase is again solid, mobile phase is liquid. Step is to select a stationary phase. So most commonly silica or alumina is selected. Then you have to pack the column, dry or wet packing. There are two types of packing of column. The next is selection of the mobile phase. So mobile phase should be a non-polar if the stationary phase is polar. You need to take a mobile phase in such a way that it should not interact with the stationary phase. Alright. Firstly, column is packed and less polar or non-polar eluent is poured from the top of the column, and elution is done to collect the separated column. So isocratic is single mobile phase, and gradient which has multiple mobile phase. So you can see this is how a column chromatography looks like. So it's a kind of burette which you can see, that's called as a column. Yeah, so in this you put the stationary phase, which is generally silica or alumina, and that's your isolated sample, and then you pour the mobile phase. As the mobile phase will move, you can see that your the sample is, which was earlier a loaded sample, that is separated out, right? And at the end of the time you will see that this whatever this separation is, that will come first out of this particular column, and that's how you can separate out both of them. So that's the benefit of it. This is ion exchange chromatography. I hope you all have heard about ion exchange chromatography. It's one of the topic which you study in your lanthanides and actinides as well. Here the mobile phase is buffer solution, stationary phase is solid, generally resin beads, and charged molecules are separated, and it is based on the electrostatic interaction. So resins are small beads carrying a charge. So positive beads attract negative charge and negative beads attracts positive charge. So you can see if you have a positive charged beads, and if you have the solvent which, or if you have the sample which is having both the charges, plus and minus charges, positive and negative charge. So what will happen, that the negatively charged ions are going to get attached to this particular bead, and the positively charged compounds is going to come out of it. After that you can apply some other like eluents, so that your negatively charged ions can also come out. So that's how you can separate out the charged ions. The steps are like, first step is called equilibration step. In this it's a kind of like blank determination. Okay, so no sample is added, only mobile phase is running and is detected. Second thing is loading of the sample and is in the calibrated column. So the first step is to equilibrate the column and then to load the sample, and the third step is to washing the unwanted molecule by the buffer. Okay, so the unwanted molecules will be washed away by the buffer, and the fourth is to do the detection. So the absorption is plotted. So this actually is this whole ion exchange chromatography is connected to a computer, and all the data is plotted over there. So this thing will be done in your system or in your computer. Okay, so absorption versus the time is plotted. So you can see that this is the baseline. So once the column is equilibrated, then you will get a peak. So these are all unwanted molecules. Then this is the elution. Okay, and after that the tightly binded compounds will come out. So first this peak means your, first of all, elution means the first when these positively charged proteins or positively charged ions are coming out, that's what is elution. Okay, so that will show a peak, and then those which are more strongly packed or more strongly bound over there, they will also come out at the later time. They will take more time or more volume to come out of it. Okay, so that's how it is being plotted. So yeah, that's what is ion exchange chromatography. In the ion exchange chromatography, we calculate ion exchange capacity. It's the total of active site of the resin in which ions are attached because of the greater molecular weight. So IEC is equals to volume, that is in ml, multiplied by the molecularity divided by the mass of resins in gram. Size exclusion chromatography is also one of the method, and here mobile phase is liquid, generally phosphate buffer, and stationary phase is resin beads with microporous structure. It's a kind of column chromatography. Here size play a very important role here. Okay, so molecules are separated on the basis of their size. So remember, in size exclusion chromatography, size is the factor. In the ion exchange chromatography, electrostatic force or the charges are the factor. So here porous beads are there, you have small permeating molecules and you have large excluding molecules. So when you are going to pass it, of course your small permeating molecules are going to stay as it is, whereas large permeating molecules, depending upon the size, okay, whatever the size you are whatever the size you are providing, the smaller ones are going to come out and the bigger ones are going to stay over there itself. So here what is happening, that Vt is the total volume of the column, V naught is void volume, Vi is internal pore volume, Vt minus Vo. Okay, so that you can calculate. Vt minus Vo will give you internal pore volume. Vr is the retention volume and Kd is the partition coefficient. So the equation for this becomes Vr is equals to V naught plus Kd into Vi. Steps in your in this chromatography are again equilibration, loading of sample, detection and elution. So first large particle are detected and then small particle. Because of a small size, they tend to go inside micropores and hence they take more time to elute. So here something reverse happens basically, as the image suggests, that what is going to happen, that a small particle are going to stay in the micropores. So these spheres are the micropores. They are going to contain the small molecules and the small molecules won't be able to move that fast, but large molecule won't be able to get stuck in these micropores, and that's why they will come out. It's simply like small, let's say if this is the road, so you are creating a small like pots, and if let's say a cycle driver and a truck driver is coming, so the truck driver will be able to go easily because he won't be able to go like the pots are not going to affect him much because of the bigger tire. And if let's say someone on skates, okay, you know skates, people walk on them, right? So this is something like this, a person can walk on it. So if someone is coming on a skate, for him these pots will affect more and he might not be able to go that easily as a truck driver might be able to go. So that is the concept over here. Small ions are actually getting stuck in the pores, larger ions are moving out, and later on smaller ions comes after a long time. So the graph is again plotted between absorption and volume. So first larger molecules will come out, that's why their peak is coming, and then your smaller molecules will come out. Okay, so the column length increases, then the elution volume also increases. Concept of theoretical plates is there, then there are hypothetical plate. More the number of theoretical plate, more will be the efficiency of the column. Narrower peak in the more efficient column. Number of theoretical plate is equals to 16 Vr upon W whole square, where Vr is retention volume, W is the width of the corresponding peak. Now factors that affect theoretical plates are viscosity, so inversely proportional to it. So viscosity is inversely proportional to the number of theoretical plates. Then temperature, directly proportional to it. Flow rate, inversely proportional to it, and the last is column length, which is also directly proportional. Next technique is thermogravimetric analysis, and it measures the amount of rate of exchange of weight of material as the function of temperature or time in the controlled atmosphere. Measurements are used primarily to determine the composition of the material and to predict their thermal stability at temperature up to 1200 degrees Celsius. The technique can characterize material that exhibit weight loss or gain due to decomposition, oxidation or dehydration. Okay, so these are the processes which can be understood or which can be distinguished on the basis of thermogravimetric analysis. In short, it is called TGA. And what information you get from here? You get thermal stability of the material, you get oxidative stability of the material, you get composition of multi-component system, you get estimated lifetime of the product, you get decomposition kinetics of the material, you can also get the effective reactive or corrosive atmosphere of the materials, and you also get information about the moisture and volatiles content in the material. This is a typical TGA graph which is shown over here. You can see weight is being plotted versus temperature. Now this blue colored line is actually your TGA curve. Okay, so TGA is shown in blue color. So you can see there is a dip in the weight. So that means there is a loss of something which is of, let's say, 10 units. Okay, so 10 unit mass is being lost. Weight percentage is there. So in calculating it, or you can say 10% loss, not 10 unit but 10% loss. So if you know the basic or the initial weight of the compound, you can find out that how much weight loss is happening. Now here again you will see that the weight loss is from, let's say, 85 or 85 to, let's say, somewhere around 60. So there is again 15% of weight loss, so on. So you can find out that what is being lost, okay, considering and finding out the mass of those. These red lines are actually the same TGA only, but in the differential form. So they are called differential thermogravimetric analysis, to DTA. Okay, so these are differential thermogravimetric analysis. So change in TGA, what does the change in TGA tell? So weight loss, whether decomposition is happening. So the breaking apart of the chemical bond is observed in the change in the TGA. Evaporation, loss of volatiles with elevated temperature. So if you increase the temperature, of course water will be evaporated and so on. So you will see dip in the TGA curve. Reduction, so if the interaction of sample is on the reducing atmosphere like hydrogen, ammonia, etc. And desorption. Desorption means if something is getting desorbed on the surface. Weight gain can also be observed. So if the weight gain is happening, in that case oxidation might be happening. That means interaction of the sample with the oxidizing atmosphere, or absorption is happening, right? Now one thing to note, that all of these are kinetic processes, that is there is a rate at which they occur. Now because most of the events that occur in TG are kinetic in nature, meaning they are dependent on absolute temperature and time spent at that temperature, any experimental parameter that can affect the reaction will change the shape, transition, temperature and the curve. These include, means what are the things which can affect the TGA curve? The first thing is pan material type. Pan material means in which the sample is kept, that thing, okay, so that is called pan. So pan material type, shape and size. The second is ramp rate, third is purge gas, and fourth is sample mass, volume or form and morphology. So these are the things which can affect. Now there are different types of pan like platinum pan, aluminum pan, ceramic pans are there. Ceramic pans are generally used, so you can see them, okay, and their temperature ranges are given, that up to what temperature they can be used. Now you can see effect of the sample size. So if you increase the number of sample, here it shows that you are actually increasing the sample weight. So you will see that the graph or the dip is changing, right? The TGA curve is changing. Here is the effect of heating rate. So at different temperatures you will see different dips. Here is the effect of mass. So if you change the mass, your TGA curve is also going to change. And this is the effect of the sample morphology. So if you change from amorphous to the crystalline form, your TGA curve is also going to change a little bit. TGA in the differential form is called DTA, that is differential thermogravimetric analysis. I already told you about this, and it can give various information at a time. So if this is a TGA curve, the blue one, that means it shows a dip, that means a dehydration is happening. Exactly at what temperature it is happening, for that you can calculate DTA. Okay, so DTA is going to tell you that. Alright, so these were certain things from your analytical chemistry, and these were certain techniques. There is a lot of things to be discussed in analytical chemistry. I just included some of the part from where general questions are asked in your CSIR net exam, and I just thought that I should make this video before exam so that it might help you in the upcoming one, right? So thank you so much for watching, and do let me know in the comment sections below that if you want some specific topic for me to make on single shot video. Remember, see topics like quantum chemistry and all, these are very vast topics. It's very difficult to make a single shot video on them, but still I will try to include as much topics as possible before your CSIR net exam. So thank you so much for watching this video. I will see you guys in the next one. Until then, have a great day. Bye bye. Take care. Hey guys, so I teach live on Unacademy Plus platform. Here I teach for the CSIR UGC net category, and you can follow me over here for regular classes. You can access my free classes as well as my paid classes on this particular platform. The classes which are free, you can get that under the section of special classes, whereas in order to access my paid classes, paid live classes, you have to take Unacademy Plus subscription. So do make sure that you take the Unacademy Plus subscription to access all my paid classes, which are quite organized. The whole syllabus is being completed over there, and the classes are quite regular over there. So make sure that you take Unacademy Plus subscription by using my referral code, that is N_Huda. That's it for this. Thank you so much.